Hello everyone, welcome to the presentation about this position paper titled Towards Model-Driven Quantum Software Engineering. My name is Antonio Garmendia and I'm the co-author of this paper together with Felix Gemeinhardt and Manuel Wimmer from Johannes Kepler University, Linz. The agenda of this presentation will follow this structure. I will start with the introduction and background of model-driven engineering. After that, my colleague Felix will continue with this presentation giving some introduction about MDE application for quantum computing, the demonstration case with the initial results and lessons learned, and lastly a research roadmap and further steps concerning future challenges regarding the application of MDE to quantum computing. Nowadays, we face an increased use of quantum computing. Therefore, there exists a vast amount of quantum computing framework, programming languages, platforms. Developers that use these technologies need to create real-world applications, which usually turn out to be very complex, managing, for example, a lot of qubits. The application of model-driven engineering may give us as a result an abstraction using higher-level languages. In this sense, we can apply the lesson learned from the evolution of classical programming, in which there was a development process until reaching an appropriate abstraction level such as offered by current object-oriented languages, in order to efficiently develop software systems. It is reasonable to assume that quantum computing must go through a similar process. Then, what do we expect from model-driven engineering plus quantum computing? So the efficiency increase, in the sense that we must accomplish this by writing more concise code, involve also the domain expert in the development process, and reduce the effort by using a code generation approach. So MDE is a methodology that advocates for the use of models in all phases of software development. This methodology is based on two principles. The first one is the abstractions, in which it is frequent the creation of domain-specific modeling languages, and the second one is the automation, in which the code is generated from a model. So in this example, our DSML is for creating graph representations, and from this representation we can generate a network code X. Network code X is a Python package for the creation, manipulation, and study of complex networks. Then, how we can implement a DSML? A DSML are compact languages that offer high-level primitives that usually correspond with the specific concepts of the domain. To create a DSML, developers must create an abstract syntax, concrete syntax, and semantics. Usually, the abstract syntax is described using metamodels that conforms to Meta-Object Facility MOF, which is an OFG standard, and its concepts are very close to an UML diagram. In this example, we have a metamodel that represents a social network. Social network contains persons and also the relationship between them. So to create the models that conform to this metamodel, we can generate a suitable modeling environment in which we can have a canvas and a palette to create a specific person and the relation between them. So from now on, my colleague Felix will continue with this presentation.
Thank you very much, and welcome also from my side. I would like to give now a short background on the quantum computing landscape from a software engineering point of view, and I want to emphasize 2 points in this regard. First, there is a vast amount of quantum computing approaches out there. So we have, for example, within the quantum computing frameworks, different assembler languages, different vendor-specific programming languages like Qiskit, C# or Circ. There are whole full-stack libraries and development kits. There are also universal languages, which are hardware agnostic. And there are domain-specific tools. Then there are also tools for hybrid orchestration of quantum and classical parts. Then we have several quantum primitives like amplitude amplification, quantum Fourier transform, or phase estimation. And they are on the one hand described by some code in a given programming language, and vice versa may be an element of a more sophisticated full-stack library. And a similar thing holds true for the quantum algorithms like Grover, Shor, HHL, or the variational quantum algorithms. with a VQE and QE as the most prominent ones. And these additionally may utilize one or several quantum primitives within the algorithm. And the second thing that I want to mention here is the current era of quantum computing, which we know as the NISQ era. So currently we face the problem that most real-world problems are too big to be solved on a quantum computer. And this requires the usage of so-called hybrid quantum classical applications. So first, these variational quantum algorithms, as they are parametrized circuits where the parameters are optimized classically, are referred to as hybrid algorithms. But also in a more general manner, every classical algorithm that utilizes a quantum machine for some task like solving a subproblem is also considered a hybrid application. So continuing with the possible MDE applications, so the model-driven engineering applications for quantum computing, we have now talked about the hybrid applications, which are especially promising in the NISQ era. And we've talked a bit to meet the object facility. And the question is now how to fill the gap via appropriate models and modeling languages. So within MDE, models are either created via general purpose modeling languages like UML, or with domain-specific modeling languages, which are specialized to an application domain. And these DSMLs can be further categorized into languages focusing either on the problem domain, like the one we propose in our paper with the problem domain of social network analysis, and languages focusing on the solution domain. And an example here would be a DSML that serves to ease the design of particular quantum algorithms. And the construction of DSML starts with the definition of the meta model in order to capture the domain-specific concepts and their properties. And the definition of this meta model has to happen, of course, in accordance with the regulations of the meta object facility on the meta model level. When we look one level below, we have the models as the concrete instances of the meta models. And based on such models, one can then create hybrid quantum classical applications, which are promising to yield a computational advantage. However, currently we do not know whether the existing modeling languages are sufficient to account for quantum computing. So whether they would have to be extended, whether they new quantum modeling languages have to be developed to create quantum models. Because these modeling languages would then require the ability to cope with the quantum as well as hybrid elements. And the goal of this paper is exactly to explore the subject for the case of problem-oriented DSMLs. And this is also where our work differs from related work, which, at least to our knowledge, focuses on the solution domain and therefore examines, for example, how to model quantum elements and quantum algorithms in general, without taking into account a specific context or problem, like, for example, optimization, chemistry, or finance. So we've created a small demonstration case, which shall really just serve as a first insight on what is necessary to port the existing DSMLs to quantum computing. And therefore, we have chosen the problem domain of social network analysis, or more specifically, community detection in such networks. So when we look at this graph representation at the right, this represents a social network, and each node represents a person, and each edge represents a relationship between two people. So the goal is now to find an assignment for each person to a certain community in such a way that the connectivity within the communities is maximized and the ones between different communities is minimized. So conceptually, it is about finding social groups in a given network. And on the slide, you can also see the formula, which has to be maximized in this sense. And when we look at it, we can see that it is already stated in a so-called QUBO form, which stands for quadratic unconstrained binary optimization. And this is the most common suitable form of combinatorial optimization problems for the current quantum computers. However, the problem that we face is that the instances of the real-world graphs are too big for current devices, and this requires the utilization of hybrid applications, as we've talked about earlier. So how can we model the demonstration case? As we said, the first step in creating a DSML is to model the problem domains. We have our social network with several people, relationships, and clusters or communities. The second step is then to account for the solution space, which is done via this meter model for quantum algorithms. So these quantum algorithms belong to a quantum library, which contains various kinds of such algorithms. And some of these algorithms may be further specified by one or several parameters. And the remaining part in the middle serves as the bridge between the quantum computing and the social network meter model, with the algorithm execution class as the main element. And as it links two meter models, it is considered a Wimmer model. And by using this representation, we can now deploy the algorithms with different quantum computing technologies and offer different deployment solutions. So in this sense, first the according models as instances of the meter model are created, and then the code is generated to actually create the hybrid applications and execute the algorithms for the particular problem. Okay, so in order to demonstrate the feasibility of our approach, we have applied it to the quadratic graph, which is a prominent benchmark graph in social network analysis. And in our case, the graph is represented as a binary symmetric 34 times 34 adjacency matrix. So in our case, there are 34 people in the network, and the matrix element just indicates whether there is a connection between two people or not. And on the solution side, we've utilized three algorithms for this demo case. The first one is based on quantum annealing, and the second and the third algorithm utilize gate-based quantum technology. So the GB1 just iteratively finds the strongest community within a graph and removes this community and stores it. And this procedure is just repeated until there is no more community left. And the GB2 is just a recursive bipartition of the original graph. The quantum providers that we have utilized or that have been chosen are IBM with the KISS-Kit software development kit for the GB1 and GB2, as well as the D-Wave quantum devices with the Ocean software tools for the QA1 algorithm. And finally, the deployment model was defined and a code generator, which was based on extent, was implemented. And the Eclipse series has been used as a graphical modeling environment. So what are now the lessons learned from this demonstration case? First of all, in our case, we have utilized very problem-specific algorithms that have been known to us in advance. And this raises the question of how to do a proper mapping between the problem at hand and the available solutions for the problem. And this may need a proper orchestration and modeling of the potential algorithms together with the data structures and the complementary classical tools and services. The second point deals with the question of how to model algorithms utilizing quantum elements if no one is available for the problem of interest. And if a new algorithm has to be designed, one has to consider a potential trade-off. Shall the algorithm be more generic and modular, or shall it be more specific and useful for the particular problem? And a possible solution here would be to replace the generic parts of an algorithm with the specific ones based on the knowledge about the problem and the backend in the sense of using refinement models. When it comes to the problem inspection, different vendors use different tools, which also raises the question of how to perform the abstraction step to model-driven engineering. And what we've also noticed is an increase in efficiency in terms of experimentation with the various approaches. However, our proposed model considers just one single task. And in a more generic and holistic approach, according workflow models and orchestration tools would be necessary to represent the whole task chain. And lastly, we recognize that not only MD could be applied to quantum computing, but rather can quantum computing be applied to solve hard model-driven engineering tasks. So in this sense, the community detection problem can be projected to the modularity maximization problem in software engineering, where one wants to have a big system being structured in modules in such a way that the coupling between models is minimized and the cohesion within single modules is maximized. Okay, so based on this demonstration case and the according lessons learned, and I want to continue with the research roadmap, which includes some major challenges that have to be overcome. As we've seen, a holistic MD approach would require a way to account for according quantum data transformations and modeling quantum algorithms themselves, besides just applying existing ones. But there's also the question of how to consider hybrid algorithms and which extensions in modeling languages are necessary for this purpose, of course. Furthermore, there are code generators, and such code generators rely on patterns and standardized ways to represent certain problems and solutions. And they would also require repositories of quantum and hybrid algorithms, together with the optimized procedures to select and apply these elements. And this raises the question of how such processes can be modeled and reused in a code generator. The third research question deals with the cloud-based deployment of quantum computing. And here existing modeling languages for cloud computing may have to be extended to account for the deployment and integration, especially of hybrid algorithms. Then for creating executable DSMLs, the problem of testing and debugging is crucial, and it is even more complicated in the quantum computing domain, because any measurement during the computation would destroy the superposition state. And as different vendors offer different tools for the problem inspection, a question of how to perform the abstraction has to be asked. The fifth research question refers to increasing the efficiency of experimentation with quantum technologies via MD practices, like, for example, an automated data generation from models. And therefore, the modeling environment may serve to run domain-specific studies on quantum technology, of course, provided there are feasible DSMLs for this purpose. And the last research question does not ask how MDE can be applied to quantum computing, but rather how quantum computing can help to solve hard tasks in MDE, such as, for example, model transformations or model-based optimization. Okay, to summarize, we have shown a small demonstration case for applying model-driven engineering to the quantum computing domain via dedicated problem-oriented DSML for the community detection problem. And we've presented some resulting challenges to further explore this topic. And in this sense, I would kindly invite the community, to take the next steps together and build according repositories for MDE applications. And this would include, on the one hand, exemplar templates like the one outlined in this presentation to explore how to apply MDE on a conceptual level. And on the other hand, there will be a reference applications that serve specific implementations as a basis for further abstractions. So our focus will be still on the problem domain. So our future research will go into the direction of constructing a DSL and workflow models, especially for the domain of quantum combinatorial optimization, especially on these devices. In this sense, thank you very much for your attention, and I'm looking forward to the discussion. Thank you.